the normal distribution. So I like this little, they call it the bean machine, and you drop a ball at the very top. Whoop, drop a ball at the very top, and there's just as much, odds are it's going to come right down the center, right? That's where most of them end up. But it's just as much probability as it going to the right of the middle as to the left, right? So they call that a normal distribution, or a what curve? Bell curve, maybe you've heard of. So it happens in nature a lot. They call it a Gaussian curve too. Okay, and Dr. Math has his ideas of what's going on here too. But this is the type of, as long as what's going on, you're not, when you do a measurement and you never get the exact, because it's real life, you never get the same answer twice. But if you're measuring the same thing over and over and over, just doing the same thing, like this pencil, put it on the balance and mass it. Write it down. Put it on the balance and mass it. Put it on the balance and mass it. Same thing over and over and over again. I should get a very narrow or a very wide distribution. Here's a distribution, this white plot. What would it look like? Should it be very narrow or very wide? If I mass this pencil again and again and again. It should be really narrow, right? I mean, look at this fancy little balance. He should be giving me, he's not going to be bouncing around too much. As long as, I don't know, Marlena isn't, right? You're doing stuff. Because that wouldn't be random. Then you're throwing out the normal curve. Because now she's breathing on it, now she's not. Now she's breathing on it, right? It's not random anymore. So it needs to be random. And you see little digits bouncing around when you use those analytical balances. It's random at the end. So that's Gaussian. That's a normal distribution. But very often you don't want to measure just the same thing over and over again. It's more like a real life situation. You've got a bunch of objects, like in this pencil box, they're supposed to be identical, right? So let's mass each one of them individually. Now our distribution might be a little what? Wider or narrower? A little bit wider, right? Because there should be more variance. But still, if the reasons why these guys all don't have the exact same mass, if it's random, and usually it is, usually, right? Then you'll follow normal distribution. What gets interesting, though, to me, is let's make up a story. Look at all this chalk by the Prang Company, okay? I have no idea about how to make chalk, so I'm making all this up. But I do know what the compound is. What is chalk? Calcium? Carbonate. Okay, so Mr. Prang here has, someone bought a bunch of his chalk, and they, at the Our Lady of the Lake, just installed brand new chalkboards. Shoot. There's a hunk of iron, little chip of iron in my piece of chalk. You scratched up my chalkboard, Mr. Prang. So you go call him. It's a real problem now. He's got chalk, he's got iron particles in here. So how could he kind of quantify what this problem is? Do I need to go and do I need to tear apart my whole factory and figure out this iron problem? Or is it just one chance out of, is it a 0.001% chance that this Our Lady of the Lake got this one bad piece of chalk? If it's a 0.001% chance, hell, I'll buy some new chalkboards, right? It isn't worth the trouble. So what are the odds? So how would he figure out this 0.001%? Well, he'd have to figure out some way of measuring the problem. I'd say mass would be an easy one, right? So he'd mass every bloody piece of chalk coming off his factory floor. Find the mass of them, right? And then make a distribution. Make a distribution. And then he can ask the question. His lawyers are going to say, you can handle a 1% chance. Or you can handle a 0.0, because it's a lot of chalkboards, right? If 1% of your chalk has these iron particles in it, and you end up paying for it, you can afford it. So his question would be, whoever's running his factory, okay, what are the odds of this being bigger than 1%? That's a huge and important question. You're going to learn that today. I mean, that's power. That, to me, there's a lot of power in what we're doing today. You can answer questions like that. So let's see how this is going to get done. So here's questions, like I was trying to get at. What is the probability of getting a result bigger than some number? What's the probability of getting a result that's less than some number? What's the probability of getting a result between two possible numbers? Right? And put all of these in terms of a real life scenario. It's infinite. Okay? So to answer these questions, you need a lot of data. Right? And when you get a lot of data, you're doing, like, think of all this chalk. What's two statistics that you could probably calculate? If we massed every piece of chalk, what's two statistics that you've heard of you could probably calculate? One would be all these individual pieces of chalk. Just calculate the what? The average. Calculate the average. That's going to be an important statistic to figure this stuff out. What's another one? Starts with an S. This one, maybe you've calculated maybe once or twice in your life. Standard deviation. Standard deviation is a measure, when you calculate it, big fancy equation, all that is how wide is this? That's what standard deviation is. Average is going to be the center of your distribution. The standard deviation is going to be a measure of how wide it is. So those are two statistics, and if we measure those two, that's really all we need to answer a lot of these questions. But let's get started and see how this works. A histogram. Pretty much that's what you got to make. You mass out all these different pieces of chalk, and you plot a histogram. Now, in a histogram, Kelly, you plot what versus what in a histogram? You have the y-axis and the x-axis. What do you plot if you want to make a histogram of all this data, of all these chalk? Not time. The values. All the values would be down here. I like that word values, right? Maybe we should use the word measurements, though, because that's what we're supposed to be doing. We're supposed to be making measurements. So. But I like values because it's more numerical. But let's say all the measurements. All the measurements is what that's supposed to say. What do you plot on the y-axis? You're making a histogram. Frequency, frequency means you have to divide it by something. Pretty much just tally. It's kind of what he means, I think. The tally. Remember the word tally? Remember doing a tally? Oh, it happened once, twice, 3, 4, 5. Remember doing that? The tally. How many times it happened? Okay. I guess you can kind of say the word frequency, but I think of the term time when I think of frequency. But tally would be, I think, would be a better word. The tally. And then you plot it all out. So assume a histogram, Kimberly. Assume a histogram of results is created using an infinite number of measurements. The histogram contains blank of the possible results. Anybody help her? Oh, you just did it of all the measurements, right? So sketch the obtained distribution on the above plot for such a histogram. Okay. Well, it needs to be, the highest peak would be in the center, right? And just kind of try to make it as symmetric as you can. I don't know, it's not very symmetric. But it should be perfectly symmetric on both sides is how you should draw this, right? Label locations of the standard deviation and the average. So, Gloriana, where would you say the average is located? In the middle. What symbol is used for average, Ricky?
X with a bar on it.
X with a bar on it. Good. X with a bar is average. Okay. How about standard deviation, Danielle? Where would you indicate? So here's my average going right up the middle. Where's my standard deviation? Where would you draw that at? Yeah, it's going to be width. Now where? Because look, the higher you go up, the narrower it is. The farther you go down, the wider it is. So where is the standard deviation at? She's right, but where? At exactly what height? At exactly, not the lower part, not the upper part, at exactly the middle, half. Go half of the height. So if you can find half the height here somewhere, it needs to be exactly half the height. That width is the standard deviation. What's the symbol for standard deviation? Not x bar, that's average. Sigma. Sigma. That's standard deviation, little sigma. Okay. So Jackie, we make any measurement, then the probability of exactly matching that measurement with one in this distribution is what percent? What's the probability? Mass a piece of chalk. Oh, it matches exactly something in the distribution. Probability would be 100%. Right? Because the distribution has everything. Whatever you measure, it has to. Otherwise, your distribution isn't complete. Okay. Select a range of results in the above distribution and shade in the area under the curve that corresponds to the selected range. Okay, so let's pick a color here. Purple. I want to be, let's do this one, between here and over here. So maybe a little bit below the average and a little bit higher than the average. That's just my range that I'm interested in. Pick a real life scenario that fits that, and that, right? It could happen. So those are the values that I'm interested in. And that said to shade it in. Fine. Shade it in. You just pick a range. Doesn't matter which range you pick. I'm just picking anything randomly. Okay, and I shade it in. What does the shaded region represent? Andy, what does that shaded region represent?
It represents the probability of matching one.
Represents a probability matching
X or Y.
matching a measurement that's in the shaded region. So area is probability. Area is probability. Okay? Shade it in. That's a probability. Right? So to get 100%, you have to shade in the entire curve, right? Well, we didn't shade in the entire curve. We shaded in, what percent? It looks like more than 50 the way I drew it. So maybe 50, 60%. I don't know. Okay, you'd have to actually figure that out, what that area is. If the entire area under the curve is shaded, Melissa, that would correspond to what? 100%. Okay. So in order to determine probabilities for ranges of results, plotting histograms of all possible results and shading in is ridiculous. You don't have time. So instead, when it comes to normal distributions, just replace the blank axis with a blank axis. Where is this coming from? Replace the x-axis with a z-axis. Okay, now what is this z? Now, you don't have to really memorize it, because if you look at the bottom of one of these charts, it's defined for you, but you have to have really good eyes. All right? Can you see it? X minus x bar over sigma. Right? Isn't that what it says? Oh! I just jumped over something. Good eye, Jackie. Okay, you look down here, you see a mu. I didn't write mu. I wrote x bar. If you've had a statistics class, what's the difference between mu and x bar? They're both averages, except one. Does anybody know? One's the population. What's the population? This thing is the population, your distribution, every possible measurement. Make every possible measurement, every possible one. Find the average. You're not supposed to write x bar for that. You're supposed to write mu. You go to lab and find an average. Well, you better not use the symbol mu because you didn't do this an infinite number of times. You can't use mu. You have to use x bar. So that's why I wrote that. Thanks, Jackie. I'm glad you noticed that. Okay. So, whoa, how do I have all these x bars in here? Okay. Okay, so if we make this, so we make that substitution, you have to know what the average and what the standard deviation is. Each measurement, it's going to take a while, right? Take each measurement, subtract the average, divide by the standard deviation, you get a z. So you'd plot what versus z? The y-axis didn't change. It's still tally. Or if you like the word frequency that Ricardo was using. All right? So nothing really changed. You have the exact same plot here. Now I can't draw it. How do I do that? Draw nice and symmetric. Nice and symmetric. It doesn't really help to say that. All right. So here's my distribution now. Z-axis and tally. So I replaced my x with z. What would this z be? What's the number right here in the very center? What would it be? Z equals what number? The very center. Because remember, what was in the very center was the average. So in the very center, x should be x bar. Right? That's kind of what we said. In the very center, there it is. X is x bar. Well, if x is x bar, substitute it in there, divide it by sigma, you get what number? So x has to be x bar minus x bar divided by sigma, you get 0. So in the very center now is z equals 0. So that means you're going to have a bunch of positive z's and a bunch of negative z's. All right? And it goes all the way to infinity. This keeps going. Okay. So no longer are we using actual result. You can use an actual result here if you want. You just have to go back and use this equation and calculate it, right? Because z is your measurement minus x bar all over sigma. So if I give you a z, z is 0.7. Well, then you plug in these numbers and you solve for x, you'll know what the measurement is. So that's how the system is working. Okay, you with me so far? So we don't have tally versus x anymore, tally versus the measurements. We have tally versus z. And in the very center, z equals 0. So let's see how this particular change in axis will actually give us the probabilities for different ranges of measurements. Boom. The answer is really in this table. This is where all the answers are. We have to learn how to use this table. So do you see how they have z column? Now this y column, that's if you actually wanted to plot it out. I don't really think you need to worry about it. Well, we're interested in this area. Because area corresponded to what? Probability. And that was all of our answers. What's the probability of it being above the average, being in this range, being above a certain number? What's the probability? We're after area. Okay. Let's practice a few of these. Sketch the answer and provide a numerical value for each. What is the probability of a measurement that'll be greater than the average? So what I mean by sketch the answer, because life is going to get much more complicated. So it seems like a waste of time now, but it really won't be. So draw your distribution. It's getting worse. Draw your distribution, right? Shade in the area of your answer. How would you shade in the area, Monica? What would you make it look like?
You would draw the average line and then shade in everything to the right.
Yeah, shade in everything to the right. Okay, now remember that dashed line, Brandy, is really z equals what? Yeah, the average. Or z equals 0. Z equals 0. Okay, so there's my answer. But, you know, you can't show Naya, yeah, here's your probability. You got to give an actual percent. What would you say the answer is? You just shaded in what fraction? 50%. We don't even need to look at the table. I mean, you shaded in half. It's 50%. Okay, so when we can't tell by looking at our sketch, we're going to have to go to the table and learn how to use it. So let's jump down here. What is the probability of measurement be between z equals 2 and z equals 0? Okay, so draw your distribution. Boom. Okay, that's my z-axis, my tally. Between z equals 0 and z equals 2. So Naya, what'd you shade in here? How'd you do this? How should we do this? Shade in between z equals 0 and z equals 2. What would it look like? Select down the line. Perfect. That's where I would start too. There's my 0. Okay. Yeah, put a line around 2. Who knows where it is? You do it, right? And then she says that's 2. And then she said shade it in. That's our answer. Okay. Now, Jeff, I can't tell what fraction of the area that is, so we have to use the table. So check out the table. Right? Where do you see z equals 2? You can't really see it. You probably have to look at your notes to read the table. At z equals 2, what's the area? 0.4773. Okay, that's the area for z equals 2. Now 0.4773 is the same as what percent? 47.73%. Okay. Now what we need to realize is how these areas are defined. And it doesn't say it in the table, so you have to know this. All these areas are defined between z equals 0 and you pick the z. So if I want to know the area between z equals 0 and z is 0.1, that's how I look up 0.1, I'm done. If I want to know the area between z equals 0 and z equals 2, well, then I look up the 2. And then I'm done. There's my answer. So all of these areas that you see on here, like the 3.7, that's for the area under the curve between z equals 0 and z equals 3.7. So remember that. If you remember that, we can figure out this one. What's the probability measurement will be between z is 1.5 and a negative 1? So Desiree, how should I sketch this in here? This is my z. How would you sketch this? Oh, I forgot to draw that. Yeah.
Now put the 0 in the middle.
Put the 0 in the middle.
And find -1, which is 0.
Good. Negative 1 over there.
And then 1.5.
And 1.5. And then shade it in, she says. Okay. So Sabina, we got to figure out what the area is of what we just shaded in. What would we look up? All right. How could we do this? Now remember, these areas are between z equals 0 and that number. Yeah, perfect. 0.4332. So that, did you hear? That's 0.4332. That's this area. That's a 0 and 1.5. Marlena, oh, dang it. Are we missing a table? There's no negative z's. We don't need one. Why? Use the one. Why? Because the normal distribution is perfectly symmetric. So you don't care, right? So she said use the 1 for the 1. Where's the 1? I can't read that. Is that 0.3413?
Yeah.
Okay, 0.3413. Okay, so you add those up, you get about what, 77%? Something like that?
77.45.
77.45%. Thank you very much, Mark. Whoa, that's up here. Not there. Okay. You do this one. Try number 4. Try number 4. Do you have a game plan how to do it? Kelly, do you have a game plan how to figure this one out? All right, hopefully you shaded in the area between 1.7 and 2. How could we figure out the answer there? Do what? Anybody know? Subtract. Because you find the area for a 2, that's going to be this whole mess. Find the area for 1.7 of that mess. Subtract the 2 exactly, and you'll be left with the answer. The answer you're interested in. All right. And Ricky, the answer is
2.19%.
2.19%. Now, if you wrote the answer as 0.00219, that's fine. Just you better not have a percent symbol by it, okay? Because both of them are identical ways of writing percent. So we're okay so far? Stop me. All right. Now you knew it was getting too easy, don't you think? What is the probability of measurement will be between 1.78 and 2.09? Okay. Blow this up a little bit. Let's blow it up over here. 1.78 and 2.09. That's what I want. Okay. Are those numbers in the table, Gloriana? No, they're not. So we have to do the I word, which everyone loves. What I word am I talking about, Ricky? Interpolate. Okay, so how are we going to do this? Everyone's got their own little way of doing it. My way is a way that I can remember it. I'm going to take a fraction of the known interval times the area of the known interval. Okay, so what do I mean by that? The fraction of the known interval. What's this known interval thing? Well, I know the just like I did up here, I know the answer if it was 1.7 and 2.1. It's not though, but if it was, man, I'd be set. There's 1.7, right? That's the one just below it. And 2.1, I could get that answer. In fact, if you didn't want to interpolate, that's usually what we end up doing on tables. We don't interpolate. We just take 2.1 minus 1.7 and say, that's close enough, right? I mean, you do that especially with temperatures. Right? That's close enough to 25. But anyway, okay, but that's not good enough here because dudes are going to get sued if you don't do this right. So what we want to do is get the fraction of the known interval, and you can already see what it is, right? I want this part. So 2.09 minus 1.78 divided by 2.1 minus 1.7. That'd be the fraction of that interval, wouldn't it? Take 2.09 minus 1.78. 2.09 minus 1.78. You got to see this, otherwise it's not going to make sense, right? This length divided by the total length. This short length is 2.09 minus 1.78. The entire length is 2.1 minus 1.7. There's my fraction. Does that make sense? You want to conceptually see it. Don't memorize it because you're going to get so lost. Don't memorize it. Sketch this guy out and then just look at the fraction. You want to, first you sketch out what you're interested in, the 1.78 and the 2.09. Draw it in. No, it's not in the table. Shoot. Okay, fine. Go to the one that is in the table, 2.1. Go to the one that is in the table, 1.7. Write them down. And then you can see your area, right? You want to compare this length with the entire length, right? Divide those two lengths. That's all you're doing. 2.09 minus 1.78 and 2.1 minus 1.7. Okay. Then times the area of the known interval. Well, that's just like we solved the one above it, number 4. Take the area for because what's this entire area of this chunk of cheese right here? You take the area for 2.1 and then do what? Subtract the area for 1.7. That's how you would get the area of that known interval. So that 2.1 is 0.4821. Minus 1.7, 0.4554. .4554. And we will get our answer. All right, try it. A lot of parentheses. Use a lot of parentheses. Hopefully you're not writing anything down. Do it all in your calculator and trust it. And you got what, Mel?
2.07%.
Perfect. Or 0.0207 if you don't like to write percents. 2.07%. 2.07%. Make sure you can get that. Regardless of the calculator you're using, you're going to have to use parentheses if you don't want to write anything. Okay. Here's another one. What is the probability a measurement will be greater than 1.587? It's not in the table. But this is a very typical question, right? Because you're worried that whatever you're doing is going to be bigger than some number, because that's the problematic thing. So this is a very common thing. So in the distribution, you sketch it out. Again, I strongly suggest sketching these out. Write in, I don't know, 1.587, shade it in. But to me, this type of sketch doesn't help me very much. I like this type of sketch, right, where I can actually show the above and below and I can see my fractions and things. Right? First is this, do you agree with I shaded in this everything bigger than 1.587? Okay, so let's make this type of sketch though instead, where you have, it's really zoomed up. So you have your 1.587. Okay. But what's the next number over? See, I don't know if you can see the issue here. Let's finish it. I'll show you. I'll show you what I mean. The problem is, let's say this is 1.6. What I want to get, what I'm going to have to do with these that are kind of going to infinity, you have no choice. You have to, this whole area is going to be what percent? This whole half of this would all the way down to z equals 0 to infinity here. That's what probability? 50. So what we're going to have to do is, because we know z equals 0 is in the table, we can handle this side. So we have to treat it this way. What's the probability of it being less than 1.587? That's what you have to do first. And then subtract your answer. Let's say you get 0.4. Then you got to subtract it from well, the whole thing is 0.5. So if you get 0.4 for it to be less, well, 0.5 minus 0.4. What I'm saying is we can't do these calculations on going greater than. We have to do less than. And then we subtract it from a half. Let's work this out. So again, the same idea. Fraction of the known interval times the area of the known interval. Fraction of the known interval, right? Oh, here, you guys write it in for me. Do you see that I want to go less? So if I'm shading this in, it would actually look like this. This is really what I got to find first, all the way down to z equals 0. So the fraction of my known interval. Remember, you take the, what's the entire length? The entire length is from 0 all the way out to 1.6. All I'm interested in is 0 out to 1.587. So the fraction would be, you know, like the smaller length all over the entire length. The smaller length is 1.587 minus 0. The entire length is 1.6 minus 0. So again, what we're after is the probability of it being less than 1.587. And then we'll subtract our answer from a half. The area of the known integral, well, what's the area from 0 out to 1.6? How do I get that? Look it up in the chart. And 1.6 is 0.4452. Okay. So we're stuck. With this table, that if it had a weakness, I'd say this is it. Because now you have two steps. Well, it's not that big a deal, but you get an answer here, it had better be less than a half. Otherwise, you really did something wrong. Okay? So you get an answer, then you subtract it from a half, and you'll have the probability of it being greater than 1.587. So this is the probability of being less than 1.587. So our answer is really going to be 0.5 minus the probability of it being less than 1.587. So that's 0.5 minus, I don't know, what do we get here? What is it? 0.44. Sure, why not? That's okay. That's good. All right, so take that minus that, you get about, what, 6% is the final answer. And it should be dinky, because we're talking about only this little shaded area out here. Okay? And there's always more problems than we can cover, but it's the same idea. Okay? I always give a lot more than we can cover. But make sense?
Question.
Yeah.
Up there, how come we went with 1.7 instead of 1.8?
No, if you did 1.8, sketch it in here. You'd be cutting off part of your needed answer.
Okay, so we're going to take the outer bound.
Yeah, you got to take the outer bounds. That's a really good point. Do you see Ricky's question? He's saying go back up to number 5. 1.8 is a nice round number, but if you picked 1.8, right, you'd be cutting off, you'd be losing some area. So don't pick 1.8. You got to pick something outside, below and above. So give them a